Right, so good afternoon, everybody. Thanks for attending our Ansys OptiSLang webinar. We have Rene Kalmeyer from Ansys who's presenting this for us today. He's taking us through this for us in Southern Africa at Hugensoft. We definitely see OptiSLang as a new tool that we can introduce the industry to. And from our side, we just want to say how we see it. It's a leading edge answer to some challenges that our existing CAE base have based on design optimization. So over to you, Renee. I don't know if there's any other comments from anybody in the audience at this stage, but Renee, you're welcome to start. Thanks a lot for everybody's time. And Renee, you can go ahead.
Thank you. And therefore, I would also now share my screen. That means, can you give me a short hint if you can see my screen?
Yes, we can see it.
Okay. Then at first, thank you for this introduction, and thank you that you're joining to today's first webinar regarding OptiSLang. And I want to introduce you today some OptiSLang capabilities. And OptiSLang stands for this process integration and design optimization platform. And therefore, maybe a first quick look, if I go to the presentation mode, to my person, that means I'm René Kalmeyer from Ansys Dynado. I'm now with Ansys Dynado since 8-9 years, and since the acquisition in 2019, Dynado is in the Ansys family. I'm located in Germany, and before the acquisition, I was the quality manager of the software OptiSLang. And after the acquisition, I'm a product sales specialist. That means working together with customers and see where we can help with our OptiSLang capabilities. And therefore, it's nice to present you today something about OptiSLang. And I said it before, this is only now the first webinar we are planning regarding OptiSLang. So you will get the first introduction about OptiSLang. Then something about how we can use OptiSLang as this tool chaining platform to connect and couple any solver you have on your side. And then also how we can make a best fit between measurement curves and simulation called calibration. Specifically, this topic will be in a third or second webinar where we're completely focusing on model calibration. Then some other topic is design understanding, where we want to show the ranking of sensitivities, most important, less important, unimportant input parameter by using our sensitivity analysis. Then we want to go on with some improvements. It means how we can improve the assembly, the design by using optimization strategies. Something about manufacturing tolerances, how we can include this information and how we can check the robustness, how we can check if we have a sigma level, maybe a 3, 6, or how we can check the reliability. And then also something about how we can use all these capabilities from OptiSLang to create a better collaboration in a team, in a department, in a company, how we can easily adapt a simulation, a workflow with a nice and simple GUI, and so we can really shorten development time by using our apps. And this is a separate presentation. And therefore, maybe also a question to you, because if you have questions, feel free to directly interrupt me. I want to make it most efficient on your side. And maybe feel free, do you have some specific topic which is missing here on this list and you want to hear something, or you want to hear in a specific way something more about robustness also on? Is there some specific point I should focusing on today from your side? Okay, so it's not a specific topic, so I can in this way go on. And the first capital will be now OptiSLang introduction, where we want to show maybe you know, on the Ansys side, there's some platform unit. And in this platform unit, there is Ansys OptiSLang, the tool for simulation automation and optimization, and also Ansys Quanta, the material database, and also Ansys Minerva, the SPDM solution from Ansys. And what is now OptiSLang? Here it should be shown how OptiSLang can help in this product development process. It means at each start you have some initial design or initial idea where you want to start, and you have some given design space. And you have some goals you want to minimize and also requirements which you must fulfill. But now it's a question, which design range, which region, which optimization potential I have. And therefore with OptiSLang, we want to show if it's maybe the best way to go on the left-hand side, but maybe there it's all times maybe failed designs, or maybe not the constraints are not fulfilled. Or maybe you must go to the right-hand side, but there's maybe only some local optimal design, but you want to find the global optima. Or maybe go straight forward, and here you can find really some global optima, which is also reliable against all your input scattering. And so with OptiSLang, we want to show in the whole design space the optimization potentials you have. We want to identify the ranking of important input parameter. We want to check the robustness, the reliability, and then we want to be able to really, in a simple way, publish and reuse these all created simulations and results. And therefore, here you can see our capabilities we can offer for you. That means OptiSLang is a so-called PIDO tool, both integration and design optimization. And on the left-hand side, you can see which capabilities we offer for this topic, both integration. The first one is we are vendor neutral. That means we are nothing more like a platform where we can connect to Ansys tools, but also to non-Ansys tools, or also to some own written tools. And so we can create any tools chain you want to then let it run automatically overnight, over weekend, over weeks, whatever. And then also to enable your colleagues, maybe your concept engineers, maybe your CAD designers, to also reuse your previously created simulations. That means here we want to drive this topic simulation democratization. We want to enable with our apps that also non-simulation experts can use this created workflow. And then also this going hand in hand by using some of these analyses here, we want to create some digital twin from simulations, but also from maybe external data like measurements or production data. And therefore, here you can see on the design optimization part, we had in the first way some sensitivity analysis. This means we want to see and check what are the ranking of most important, less important, nearly unimportant parameter. We want to see which optimization potentials I have and all the system understanding of your assembly to create these things. And then we want to continue with some optimization strategies, maybe Pareto optimization, cost function plus function optimization, cost optimization and function optimization. And then also check if this optimal design is really reliable regarding the input scattering of the material, of the geometry, or of the loads. Or we can also use OptiSLang for making a best fit between simulation and measurement curves. That means maybe coming from a material calibration. And all these 8 offers here really driving this topic shorten time to market by connecting all tools together and run it automatically. Improve the product performance by using these OptiSLang capabilities from the optimizer. And also then check, is it reliable? We want to eliminate the risk by using this robustness evaluation with OptiSLang. And here, maybe in a more graphical way, I want to show you this topic process integration. That means we want to create a tool chain, and therefore we can connect to any solver, non-Ansys tools, Ansys tools, and own written tools, and then create a tool chain out of it. And here we are, they are not listed all solvers we can connect. So if you have question regarding a specific solver, maybe which is not listed here, so please ask, and then we can discuss if we can connect it to the solver. And maybe also here now some question from my side. Do you have a specific solver where some connection to OptiSLang is needed, or you want to find it here on this table? Or are you mostly some Ansys users using CFD, using Workbench?
Mostly Ansys users.
Okay, then here you see, and it's not a problem. That means Workbench, CFD, ADT, Maxwell is also not a problem. Also Alice Steiner. And if we have created these tools chain, then we want to go on with this design optimization. And design optimization means for us robust design optimization strategy. It means start at the beginning with some calibration of a material or calibration of a system, and then use this calibrated material for some variation analysis where we want to increase this design understanding. We want to create these meta models. Later on, you will see something more. And this meta model will describe the behavior between input and output. And then continue with some optimization. But in the best way, we want to optimize on this meta model so we can reduce dramatically the simulation effort. And then after finding the optimal design, we want to check if it's robust or not. And so we end up with a really optimized, robust design. So far, some question from your side. Where and in which way OptiSLang can be used? Are you familiar with these kinds of design understanding, optimization, maybe from some other tools, or are you using or doing some optimization manually or some variation study?
No, I cannot speak for the others. I did use some software many years ago, so I'm trying to see what OptiSLang can do and basically see how we can apply it on my side. So for the moment, I'm just sitting and seeing what you're showing me, and then I can make a call from there.
Okay. And therefore, maybe also here, what is new in OptiSLang 21R2? That means it's the newest release. You have heard we are acquired 2019, and at Dynado we not only developed OptiSLang, we also developed some other tools like this called here SOS, Statistic on Structure. And these things here, maybe you also know Design Explorer, all these things are now integrated in OptiSLang. And therefore, some repackaging was necessary of OptiSLang. And here you can see the packages OptiSLang Premium and OptiSLang Enterprise since the newest release. And I think it's only most important to show what is more inside Enterprise. That means if you want to drive this topic, better collaboration, easy simulation adaptation, and also shorten time to market, then this web app building is really important. If you want to work with signals, it means if you do some calibration, then normally you want to calibrate signals. Or you're working with some field data, that means some distribution of a temperature on a surface or a pressure distribution on whatever. Then you will have field data, and this is also possible with OptiSLang Enterprise. Or if you want to implement some AI techniques, this is also possible with OptiSLang Enterprise. And here we can see this is also new for Premium and Enterprise. We have now the possibility to run up to 8 designs in parallel. That means now in OptiSLang there is implemented some HPC licensing technique. This means with OptiSLang Premium we can run 4 designs in parallel. or 80 sites in parallel with enterprise. This means it's not needed to get or use some more standalone server of CFD, of Workbench or Alice Steiner. No, OptiSLang creates some umbrella and we bring these HPC licenses with us. And it's also not then needed to maybe get some or use some other HPC licenses maybe you have on your company. Okay, and now some pros in equation. That means we want to create some connection. And here maybe if you are familiar with OptiSLang, so we're familiar with Workbench, then you can create some static structural, transient thermal analysis, and you have some parameter set. And then easily you can connect all these OptiSLang modules and then let it run. And here it's really important, all these modules will have some guide, some wizard, and this wizard will guide you through all the settings. And at the end of each wizard, we have some decision tree. And please follow our recommendation because it shows you which optimizer or which DOE method is the best one. And therefore, this I want to show you directly in live. Here you can see this is Workbench. I think you're familiar with it. This is some tensile test. It means some fixation, some displacement, very simple. And here we have all the parameter. It means 5 input parameter I want to vary and some response I want to extract. And here you can see the OptiSLang modules on the left-hand side. And now double click. And now we connected. You can see here now, you can vary all the 5 input parameter, maybe from 1000 to 2000, or maybe it should be some discrete parameter. Then we also can define some discrete parameter, maybe 8, or it should be some dependent parameter. Dependent means, okay, this is all times yield stress, whatever, plus 3. And you can see here, if I change this one, then it's also changed this one. So here you have the flexibility to define all the lower and upper boundaries you want to define. Then you can go to next button. Here, input parameter, here the responses. And now you can define, do I want to minimize, maximum something, or define a constraint. So, and then going to the next button. And here now you can see the decision tree. Which DOE method is recommended from our side? And please follow our recommendation and then press the finish button. And if you want to make some optimization, yes, maybe we put in some optimization. You can see the same questions. Define the range of your parameter. Now define maybe also the maximize, minimize objective. And now you have the decision tree from the optimizer. So you can see it's really simple to create some sensitivity or some optimization by using these modules and having these guided wizards. And then you can let it run. Very simple. Here. And so this was the example by connecting to Workbench. And if you're not using Workbench, maybe some CFD, also CFD is possible. You can use CFD in Workbench, but mostly our customers using CFD standalone. That means we have some fluid connection or CFX connection. It's also available. And you must only define which inputs are founded and then use and define which inputs are really varying during the analysis and which of the responses you really want to extract. Or maybe some non-Ansys server like Abacus, also some Abacus connection is there by also understanding really important binary formats from Abacus. Or if you are more using ADT, maybe Maxwell, HFSS, QCD, then you can use it in Workbench or directly use our ADT node. ADT node especially for all this Ansys electronics desktop. Or if you are using maybe console, numerical, other things, normally we have all the connections there. And here you're completely free to connect to any server I would say you have on your at your company. And so feel free to use OptiSLang and connect to the servers. Some question regarding this process integration, because here you can see if you use OptiSLang standalone, this is now OptiSLang standalone, you have the possibility to create any complex tool chain, maybe in parallel or in serial flow. And here you can see some pre-processing, maybe some cost calculation in Excel. And if the cost calculation was successful under some limits, then really the workbench calculation is done. And in parallel, some other calculation is possible. And at the end, maybe some MATLAB post-processing. And if you have some own written tool, then it's not a problem, we can connect it. Some questions so far from the from the process integration point of view? Okay, seems not so. Then model calibration. Here I want to show only this one slider because I said it before. Model calibration will be also some separated webinar, and therefore in this other webinar we will focusing more on this model calibration. But I want to shortly explain what model calibration means for us. Here we want to calibrate a system, a material, a process. And it means you have on one hand side some measurement, some reference curves, or maybe only values, and you want to make a best fit to this curve or to these values. And here you can see it's only one reference curve, the measurement curve, and one simulation curve. But it's also possible to calibrate more than one signal, maybe also 16 signals some customers have done. And then you want to make a best fit. But with OptiSLang, we can do much more than only making a best fit. Here we want to increase design understanding, because on a signal length, you can see signal length and signal ordinate. And with OptiSLang, we can show which input parameter has some influence at which signal length. If you think about some tensile tests, then you know at the beginning of this force displacement or stress strain curve, only the Young's modulus have some influence. And then by increasing the signal length, the yield stress becoming more and more important, elastic plastic change, and at the end, some damage parameter will have some influence. And directly this we can show with OptiSLang. That means show at which signal length, which input have some influence. And this is really important, not for optimization, but it's really important to increase design understanding. And then you can make a best fit. You can also include, if you have some scattering of measurement curve, this is also possible to include. And these examples here from IFA or from Infineon and other examples, we want to show later on in this webinar. Therefore now, if there's no question from your side for model calibration, we want to continue with sensitivity analysis. Therefore, sensitivity analysis means, as I did before, you must define the input parameter. And with OptiSLang, we have no limitation. That means our philosophy is going all in. Not only 220 or 200, maybe also 2000 input parameter, not a problem. And then you must define for your parameter lower upper bounds. And then you must define in OptiSLang only how many designs you want to run. That means how many time you want to spend. Maybe 45, maybe 86, or maybe 100. And then we decide where we want to place these design points. That means we are doing the DOE for you, not some worst case scenario, not some full factorial. No, we are deciding where to place the design points. You only have to define the lower upper bounds and the number of samples you want to spend. And then every design point will be sent to the simulation, and we're extracting the responses. And then we're doing this design understanding process. It means we are creating some meta model. And maybe you know in Excel there's some regression model, polynomial regression, which will describe you the behavior between input and output. But it's really only a simple regression model. But it's clear with LS-DYNA, also with mechanical, with CFD, you will mostly have some more nonlinear behavior between input and output. And therefore, Excel is nonsense. And here we have many regression models to create this understanding about output and input. And we can give you the ranking of about most important input for the response, less important input for the response. And we can also give you some information about nearly unimportant, and all the unimportant parameter will be directly deleted. And we can give you some information about if this is the response value and these are the two inputs. Do we have only one optimization potential, like here, or several optimization potentials because you have several islands? And then later on, we want to use this MOP for some design understanding to really clear the view, to understand where I have optimization potentials, where I have all time some failed designs or some infeasible designs, and is it some Pareto optimization or not? And then we want to continue later on by using this MOP, this meta model of optimal prognosis. Therefore, here's some slide how we create this DOE. And I said it before, we do not want to use such an full factorial. And therefore, we have some so-called adaptive meta model approach. Maybe you know adaptive meshing from CFD or from Alice Steiner. It means meshing where needed, if needed. And this is the same approach here. That means we are starting with the first iteration and placing the design points. And then we are extracting the responses, and then we are creating our regression model. And really important, I said it before, these regression models going into competition. Some regression models with neural network, or some regression models like Excel, or maybe moving square or Quigging. And these regression models going into competition automatically. And then you will end up with some specific regression model. But then you will identify, here's some design point. Is this some singularity, some solver noise, some outlier, or some physical effect which I never expected? And then we are adapting only design points if needed and where needed to identify is it an outlier or not. And so we are only adding design points in region of interest instead of using it and adding it in the whole design space. And so we can reduce dramatically the simulation effort and then getting again a competition between all the regression models. And at the end, the best regression model will win. And to have some objective measurement value, we are using our so-called COP, coefficient of prognosis, to decide which regression model will win. Maybe sometimes AI, maybe sometimes moving square, or so on. Therefore, before we make a first next break, here you can see we are creating these regression models. In OptiSLang, it's called MOP, Meta Model of Optimal Prognosis. But it's also clear we can expand these techniques. If you have signals, I said it before, we can identify which input have some influence at which signal length, and then we call it signal MOP. Or we can expand it to field data, maybe 2D, like a picture. A picture is nothing more like a 2D field, or some temperature distribution on the surface, also only 2D. And then we can identify where on the location have some influence, some input, some influence. And so this drives also directly this topic predictive maintenance. And we call it field MOP, and we can also expand it to 3D field. Some question regarding this sensitivity analysis and increasing this design understanding.
No.
Okay. And therefore, if there's no question, we want to go on with the design improvement. This means to show you some success stories, how our customers improve their system. Design improvement is nothing more like optimization. That means we have done before a sensitivity analysis where we find some pre-optimized design. And then we want to go on in the best way with some optimization on our created MOP. Why? Because here, by using this optimization on the MOP, we can reduce dramatically the simulation effort, because this is some like a really advanced equation, and this is done or can be done in really in seconds. In seconds we can optimize, and if some optimization on the MOP is not possible due to the quality, then we have also many other direct optimization algorithms which we can use for optimization. And also here you can see it. It will be nice if we not only focusing on some function optimization, it will be nice if we can also implement some cost. And then mostly some Pareto optimization. That means more than one objective will be the solution out of it to really minimize the cost and also maximize the function. And here's some example for it from a mechanical analysis from Fraunhofer in Germany. So really well-educated engineers, and they optimize this structure here. That means the initial design has some initial mass and some initial deformation. That means in 3 positions, 90, 0, and 180 degree, we want to minimize the mass and want to maximize the stiffness. And so we get this project, and they want to test us, can we optimize this pre-optimized design? And so we are starting with OptiSLang, and here you can see on the ordinate value all the 4 responses, the total mass, and the displacement means also stiffness. Yeah, and here we can see on the abscissa which input is most important for the displacement, which inputs are maybe less important for the displacements, and which inputs are completely unimportant. And we can also see that for the mass, some other inputs are most important or maybe less important compared to the displacements. So design understanding to identify the ranking of most important, less important, nearly unimportant, and unimportant parameter. And here this last column shows us the overall quality. That means what is the prognosis quality of this response? And we want to have normally a value higher than 80%. And you can see it's really high quality. And then we continue with optimization. And you can see we can optimize the pre-optimized design from Fraunhofer by improving it nearly 10% for the mass and also deformation, by only using OptiSLang for design understanding and with this optimization algorithms. Or here's some nice example from Trumpf where they combine cost calculation or cost optimization with structural optimization. It means here they have such an assembly. They want to reduce the cost and the stiffness, and you can see here these dotted lines means there is some sheet in it, and you can see the optimal design. We have some less of these sheets, so we can reduce the costs dramatically by 27% and having the same really good stiffness. And here you can see we are running 10,000 design for this optimization to find this optimal design, but these 10,000 designs are only needed 5 minutes because we are running this 10,000 design, this optimization on our previously created MOP. And this is the point before. Yeah? We are starting some variation analysis. We are creating this MOP for design understanding. And then we want to continue and can continue with optimization on this so-called MOP and running 10,000 design only in 5 minutes and getting a really, really good improvement compared to the first one. And this should show you it will be nice if we can use maybe an area size, a volume size, a number of devices, and all these things are normally cost relevant. And so we can start with a cost calculation, cost optimization combined with function optimization. Some other example here, a CFD example from Rheinmetall, where they're using, I think, Fluent here in this way, and having 56 design parameter. So not so easy, yeah? And you can see the reference, the initial design. And after the sensitivity analysis, we can reduce from 56 to 15 most important input parameter. And then we are running some pre-optimization on our MOP, which was created by using some specific optimization algorithm. And then we continue with some direct optimization using some other algorithm. And you can see a really good improvement of the objective function by 38%, and also reducing the pressure drop by 45%. And you can see here reference design compared with best design after the design of experiment, it means sensitivity. Then optimal design after optimization on this MOP. It means only here, I think maybe 100 real designs. There's no real design, and then we are starting again real designs by using all times the best design from the previously analysis. And you can see the improvements over the analysis types: sensitivity, optimization on the MOP, and direct optimization. Some other example, some multi-physics example of a board is here shown. That means we want to optimize FEM and CFD analysis, where at the end we end up with I think 5 constraints, objectives, and also 12 parameters. And here you can see our so-called COP metrics again. We can see which input have some most influence on the response, less important or unimportant parameter. And we can also see how does this MOP looks like. And then we continue with an optimization, but you can see also here, we are starting with design understanding, investing 100 real solver calls to get this nice MOP, this design understanding. And then we can also condense this multi-physics, multi-objective optimization to a single objective optimization, running then 6,000 designs to continue with optimization, and then validating only 3 designs who are of interest, and then ending up with a really good improvement by only investing 103 real solver calls. Or if you are using and are more interested in optical simulations, here some example from OptiSLang with PIDO, some initial design with some contrast value of 0.8, and then optimizing with a direct optimizer. Yeah, maybe this was some other tool, some competitor. Yeah, some good improvement, but okay, we want to see if with OptiSLang, with the sensitivity and optimization, we can improve it much better. And you can see also here, a pre-optimized design can be improved much better by using OptiSLang with this technique of sensitivity and optimization. Or some other example, this was the initial design, and then the best design, much better improvement by changing this geometry here, yeah, and having some homogeneous distribution. Or if you are more familiar with HFSS, here we have some dual band antenna having 9 geometry input geometry parameter, and we want to maximize the return loss on 2 frequencies. And you can see here, starting with the red design and ending up with a better improved design from the sensitivity, but then continue with optimization. We can really reduce the return loss much better than to the compared sensitivity, and also getting some design understanding. Or if you are more for CFD turbofans, here you can see some optimization. Here we start optimization in 2 steps. At first, optimization on our MOP with 4,000 designs, and then continue with a direct optimizer, investing 200 designs, and we're having 19 parameters. And here, this should show you also the efficiency of our sensitivity and our optimization strategy. The initial design, this value, and directly after sensitivity, we have a really good improvement. And if you want to invest more, optimization on MOP validated, yes, improvement. And if you want to invest more, that means 200 designs, then also some improvement. But you can see also after the sensitivity, a really good improvement is there. And why? Because we have shown you this adaptive metamodel approach, because we are only adding where needed, if needed, and therefore we can come out of the sensitivity analysis with a really, really good design, and then you can decide it if you want to invest more, then you normally also get some more things. Question regarding this design improvement, or do you want to see some other maybe application you are interested in? Okay, so far not. Then continue with this robustness. Robustness is also a wide topic by using OptiSLang for it. And normally it's the first question, how we can define robustness. Robustness is a really wide field. And normally some really general definition of robustness is a design will be robust if it's unaffected of all random perturbations. Yeah, okay. But we need, from the mathematical point of view, a much more accurate definition of accuracy of robustness. And therefore, we have a so-called variance indicator where we said we want to check the coefficient of variation of the inputs and compare it with the coefficient of variation from the outputs. And this is from our perspective, only a tolerance check. We want to see, is the input variation smaller or bigger than the output variation? And this is nothing more like a tolerance check. Or you want to continue with a sigma level. That means you want to define a limit and you want to have a 3 sigma or a 6 sigma. Or you want to continue with really Champions League, where you want to calculate the probability of failure. All these 3 things here are possible with OptiSLang, but it's clear you need to invest some more things if you want to continue with sigma level or probability, but you will get more out of it. And here you can see in a more graphical point of view, robustness. It means in the way of tolerance check on the left-hand side and sigma level and reliability on the right-hand side. It means tolerance check means we want to see if some input scattering influence at most the objective scattering, that means the response scattering, in a high or in a low way. Or if we want to continue with some sigma level, then we must define a limit, and then we can see if it's maybe 3 sigma or 4 sigma, but it's clear here we must invest normally also more design points. For tolerance check, normally maybe 75, 100 designs are okay, like for the sensitivity, but for sigma level or especially for reliability analysis, where we want to calculate this probability of failure, we must invest more designs instead of only 100. But the way is very simple. You must define the mean value, the standard deviation and distribution type. Then we are creating the design points. You only define how many. And then we are extracting the responses and creating, like before, some ranking of most important input scattering for the response scattering, less important, unimportant, and we are creating some meta model. And here you have a list, because I'm not sure which topic you are most interested in, because this reliability is maybe a topic for ADAS, or maybe also a topic for electronics reliability. And here you can see some of our presentations together with Infineon over the last 3 years, or from STMicro, where we are focusing on electronics reliability. And therefore, maybe also this, sorry, I want to mention here, if you have done measurement data, and normally measurement data from a real geometry also have some scattering of the geometry, we can also check these input scattering about the statistical information in it. And then we can also transfer these statistical information to the real geometry. And then we can run the simulation with the real geometry scattering. This was also done from Grundfos, where they defined all the scattering we are creating this geometry and coming out with some information for them. Yes, here in this region and in this region, the tolerances must be really strict to fulfill the requirements. And here in the middle, yeah, it can be very loose to fulfill the requirements. Question regarding this robustness from your side? If not, I want to go to this topic, better collaboration, simulation adaptation or easier simulation adaptation, and also shortened development time as a last topic. Therefore, I want to jump to some other presentation. Here you can see, I put it here. And what is the motivation of the simulation democratization? The motivation is clear. It means with Ansys, you have the possibility to connect to many solvers, with OptiSLang also to non-Ansys solvers. You want to have a platform, and so you have a platform for all these tool connections, and you can run really all physics, also with multi-physics simulation, but normally it's mostly used from CAE experts. And the number of CAE experts in a company is normally really small. But in the other way, you have a really big group or number of colleagues who want to reuse, recycle. They want to benefit from these informations who are created here from the CAE expert. They want to reuse the results. They want to reuse and recycle the workflows they have created. And so it's the point one to many. That means also concept engineers or CAD designers should benefit of the previously created information. But it's also clear this democratization topic normally touches many points. And with OptiSLang, we can touch a lower number of topics, which we'll show later on. But at first, we should also check which users and roles we have in the company. Yeah? We have the CAE expert, daily using of simulations, then CAE users, concept engineers, CAD designers. And it's also clear this know-how should be published in some way. So here the CAE expert want to automate, and then they want to collaborate, and also some global deployment over locations is needed from the information, from the results they created, or from the simulations they created. And therefore, yes, it's clear the CAE expert have some really own written tools, some ACT maybe, and so he can handle it on his side alone. But how we can proceed with these other users in a company to also fulfill this global deployment. And here, OptiSLang with this both integration and this web apps can help. And in which way? This is shown here. That means a CAE expert have created a really complex CFD analysis, CAD defeaturing, complex meshing, complex single run, or maybe sensitivity optimization. But on the other hand, we have some user group. They want to have some user-friendly tool without any installation, without any knowledge about optimization algorithm, CFD settings. They only want to define what? They have their goals in mind, they want to minimize. They have their constraints in mind, they have to fulfill. And they have their maybe boundaries in mind, they can use it. And maybe they know exactly how many cores I want to use today. But nothing more they want to type in, they want to define. And therefore now OptiSLang with this OptiSLang apps can help here to use or to create such a tool without any programming. And here you can see these are now some apps, some specific apps for CFD calculations, or maybe for mechanical, for ADT, which directly gives you the possibility to easily adapt a simulation to then also reuse the results for some what-if study. And we have we make such a survey on our customer base who are using this OptiSLang apps. What is the benefit by using this OptiSLang web apps? And a big benefit was really a reduction of development time was possible and development costs. the collaboration between these different departments are becoming better and better, and also the efficiency was increasing. And also we ask them, what are the key ingredients? Yeah, the key ingredient is, I need to have some parameterized workflow. I need to make some automation of the workflow to get some standardized and reliable workflow or workflows. And directly all these 4 topics is completely 100% OptiSLang. But then we also get in touch with this topic, to really include these non-simulation experts. The acceptance can only increase if the usability is good, if the controlling, if the web-based post-processing maybe is really nice. And here we are working on the last year to really increase its usability, and so the acceptance will become higher and higher. And therefore, before maybe I can show it to you directly in live, this web service, here you can see which topics of the simulation democratization we can touch with our OptiSLang web app. That means we can work with non-simulation expert, we can create digital twins from measurement or simulation, we can automate it, and we can also connect to SPDM. But here in this way, I want to divide it in several applications. You can use these apps for some published workflow on the left-hand side, or publish what-if studies. Publish workflow means you want to adapt some simulation. You want to change the boundaries or the goals and then press the play button. But here it's clear we need to before some workflow which was created before. On the left-hand side, on the right-hand side, what-if studies means I have some ideas in mind and I want to check it. But not only from my perspective, also maybe from a concept CAD designer or maybe from the management. It means I want to input or define some inputs and I want to calculate in seconds all the outputs. It means a fast pre-calculation by using what-if studies. And also this is possible, but here it's clear we need to have some results before. That means some results in OptiSLang are called MOP, and this must create it before. And therefore, in the last minutes, I want to go to this apps. You can see here, these are my apps, and I have some specific app for this one. You can see it's all the explanation about what is inside, and now I can browse or I can change the value. So I have only the possibility to change the reference value, and then yes, I can shortly define some name and then press the play button. And then this design will be executed. You can see here it's now processing. And now this design will be executed. And you can see it here. The scenery looks like it's some fluent variation or some fluent parameterization, then the batch core fluent, and then some extraction of the responses. And you can see it here, yes, the parameterization was successful, and now it is running. I have some error, maybe I'm out of the boundaries. And therefore, you can see later on, if it would be successful, maybe I can create it again. Maybe we use it like this, maybe this one to run something again. So it's stopped now. And this one, and it's ready. Oh, also maybe I have some license error maybe today. So I cannot show it directly because here I have only the inputs, but in this way the wizards are working, or maybe some wizards for this what-if study. Here you can see some what-if study and you can read in any results you want. Right? The results will be shown here. 2 inputs are founded, and now you can define how many designs you want to check. You can define all your input values you want to check, and then maybe shortly define something else. Maybe this one. And then we can press also the play button, and all these 6 designs will be now calculated in some what-if study. And then you can see it's now stopped, and now it will be then processing. Here 6 designs are defined, and these 6 designs will be now calculated, but only on this MOP. Maybe I have really some license error because normally it's now processing all the 6 designs. 6 designs are ready now. Here successful, so now it's finished. And here now you have the possibility to see all the 6 designs in the web base, 2 input parameter, 2 responses, and you can see how it looks like, yeah, from the input side and from the response side. And so this is an easy way to really make a better collaboration, because this can be then published or hand over to some concept engineers for making some what-if study. And so you can make a really fast pre-check, or what I said before, you can run really a specific analysis to press the play button. And therefore, I'm now finished for today for this first webinar, OptiSLang Getting Started. And I said it before, we are planning also other webinars regarding model calibration and also regarding these web services in more details. If you have now some question, so please feel free. And I will send you this presentation I showed you also later on.
Thanks a lot, Renee. This was very informative, and I think there's definitely, if there's not questions now, there will be questions later on. So I think everybody appreciate your time and effort that you've put into this. Thank you very much. Is there any questions from any of the attendees at this stage?
Laura, Renee, thank you. No questions from my side. I will have to work through this again. Thank you so much.
Thank you. You're welcome. And
Great.
if you have some question, then you can contact Laura or myself, and then we can discuss in more detail what is needed on your side and how we can help with these features we offer.
Okay, so thanks a lot, everybody, for attending, and enjoy the rest of your Friday.
Thank you so much. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye-bye.
Okay.